Okay, so we talk about the Bernoulli trials. A Bernoulli trial is just a trial with a binary outcome, and we label the outcomes as 0 or 1, rather than success or failure, because later on we want to add them. So the number of ones, or the sum, would represent the number of successes in a certain specified number of trials. And we talk about this example, the binomial, and this is, we have mentioned it, but I wanted to relay it with our subsequent chapters, because here, suppose we want to estimate our P. So one estimate would be a sensible one, would be how many successes out of 10 trials in here. So this guy will estimate that the probability of getting it a correct answer is 0.7. Now, so this is related with estimation. And then later on, we are interested in, say, if he claims he has ESP, suppose the P reasonable. We do not expect him to be, even with ESP, we do not expect him to have 100% correct answer. So maybe we think that if the probability of success is 0.9 or above, then we deem him as having ESP. So it would be phrased later on as a hypothesis testing that whether P is equal to half, meaning that he is just simply guessing, versus a P bigger than or equal to, say, 0.9. So we will make some decision making based on 10. Later on, we will see that the accuracy of our decisions will commit two types of error. One is type 1 and type 2. So we will elaborate on this. But the point I want to make is these two types of error, they sort of in tension. If you want to minimize one error, if your sample size is fixed, the other error would be left uncontrolled and usually tend to be big. So it has to do with one other thing, that is sample size. So that is why in the next chapter, we will talk about sampling and sampling distributions first, how the probability depends from your sample, which your aim is to estimate your P here, and you create something like a statistic, singular, without the S, statistic, that you use it to estimate the unknown parameter P here, as well as to make a decision using that statistic to decide whether P is likely to be half versus another statement that the P is at least 0.9. All right? So we will do some of this. And similarly related to this is another kind of distribution, but the binomial is actually specifying the number of trials that you are going to do, and the binomial is looking at the total number of successes in your pre-specified number of trials. Now, whereas the geometric is different, the geometric is you do not specify the trials, and you are targeting to have the very first success, all right? And the geometric distribution look at the number of trials you need in order to get the first success, all right? I mentioned that there are two slightly different versions of the geometric. The two versions according to whether you count the total number of trials, including the one that lead to success, or you just count the number of failures in order to have the success. So very often when, of course, when people spell out the probability density function or probability mass function, then you can take a look. The telltale sign would be here from 1 onward. And so that would means basically you include the trial that leads to the success, the very first success. All right. Whereas the other version would be starting from 0. All right. But this is only provided the person spell out the probability mass function for you. If he just mentioned it's geometric with probability p, you better clarify with him whether he is counting the trial leads to success or he is not counting this. So there are basically 2 versions. Okay, now geometric means I wanted to look at how many trials I will have in order to have the first success. But the question is, why should we limit ourselves to the first success? So that leads to the next distribution, the negative binomial. The negative binomial is you have a targeted number of successes, say 4 or 5. Okay, so you will target, say, let's say I'm not interested just to have 1 success. I'm interested to accumulate 4 successes so that I would be able to decide. This happens in your subsequent example. You will see in the NBA best of 7, is it? I mean, you need to win 4 games in a total of 7 games in the final. And in other kind of competition as well. So we will do this kind of calculations a little bit later. Okay, for example, suppose we want to find the probability that the 5th success, all right, occurs in the 7th of a sequence of independent Bernoulli trials. So this slide is trying to explain how we get to this. So this is one possibility. Now, first of all, this is the last trial has to be a success. These are 2 examples, all right? And this is not only end at a success, but it also has to have 4 successes prior to it. All right, and these 2 examples illustrate this. Okay, so now for this particular case, I have a P here for success, and then I also have a P here for success. And so altogether, I have to multiply the P whenever it is corresponding to S, and then 1 minus P whenever it corresponds to F. So there are altogether, because there are 7 trials, and there are altogether 5 S, all right? And so I have P to the power 5. And because the remaining 2 trials has to be failures, is Q squared. Now, this is not it, because this is just 2 such examples. There are many other examples that will have this 5 S's and then 2 F's, all right? So the question is now how to count them, okay? So I think the next slide is trying to do something like this. Okay, the 7th trial has to be reserved for the success, all right? And then in front of you, there are altogether 6 trials, and out of which you have to put 4 trials for successes, and then the remaining slots for failures. So that explains this, all right? Now, I think when we are preparing the slide, we are explaining this, but you don't need to do this because one way that is easier to think of it is this way. Okay, so this is your 7th trial, and this is success, and this has to be the 5th one. And so out of here, there are 6 slots, and of which, because this is the 5th, so you have 4 S's, and then 2 F. All right? And so as a result, one way to think about it is 6 out of 2, and then so you have 1 minus P squared, because that corresponds to the failure, and then P to the power 4, because there are 4 successes. And then the last trial is a success, okay? So it's a P, okay? So we can generalize this into this thinking. So this is a negative binomial, K and P. K means number of trials in order to get K successes. All right? And let's say this is my random variable x, and I'm interested in x. Now k has a special meaning. Now I can't use k. So let's say m, and m is a running index. So m can be at least has to start with k, because this is the best scenario, because the first k trials all lead to successes, and then you can stop right away. Of course, you have all this. Now, of course, you can't stop, because there are some worst case, that is, you have to keep doing it indefinitely until you get to accumulate k successes. Now, so the argument is very similar to what we have just shown. So this is altogether m minus trials, and this is the mth one. And this success is the kth one. So here it means that you will have k minus 1 successes, and then now you count how many failures. So you have m minus 1 slots, out of which you have k minus 1, you put the S, so you have m minus k here. So you would have this kind of number. And so as a result, this would be m minus 1, choose k minus 1 for your success, or you can choose this, all right, because you either choose the places where to put the S, and then what is left vacant will be for F, or the other way around, you can choose places where you put the F, and then the vacant spots are for S. And so now p to the power k minus 1, and then 1 minus p, we have done this, m minus k, and then p. So the thing to remember is that when you add these two up, you will get this number. This is exactly how we figure out things, and then this power should match with this. But of course, you still have a p. The tendency, usually people clean it up in their expressions. All right, so there is an extra p coming from the very last trial. So, so that is the reasoning behind. All right. Okay, so so this kind of argument is, typical of all our subsequent calculations. So in general, we have the following. So now we use small x instead of m. Small x starts from k, k plus 1, and so on, and blah, 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 all right? Okay. Now, if you compare this with the geometric, now we are waiting for the k success. The average length, the average number of trials you have to do it is to k over p. Now when k equal to 1, you get back our geometric mean, all right? So that is 1 over p. And the variance is also k times, all right? K times the variance of that of the geometric, okay? There is a reason behind it, but I think in the interest of time, we won't elaborate on this, all right? So it's basically k times in the mean and also in the variance, all right? So if you remember this, is okay. Now, the fact is you don't quite need to remember because you can have, for exam purposes, you can have a help sheet. For working, when you're working, you can always Google it, all right? But when you Google it, especially say Wikipedia actually gives you two versions. Now, if you remember the geometric has two versions, so does the negative binomial. One version is that we are counting how many trials. This is this version. Another version is to count how many failures I have to accumulate in order to get to the K success.
Is the x minus r x minus k?
So, oh yeah, there is a typo here, right? So it should be x minus k, yeah. Thank you. So there is a typo here. This should be x minus k. Thank you. So again, there are two versions. So when you are applying the mean and the variance, you have to know what versions under which you are working on, all right? Either in the exam setting or, I mean, in work-related kind of problem. Okay. So here it relates. The negative binomial is just a the geometry is just a special case of the negative binomial when the total number of successes that you need to accumulate is exactly 1, all right? This is similar to the binomial, and the Bernoulli is a special case of a binomial when the number of trials is equal to 1. So we have a parallel statement here. Okay, so this is this. In an NBA championship series, the team that wins 4 games out of 7 is the winner. Suppose that teams A and B face each other in a championship game, and that the team A has probability of 0.55, 55% of winning a game over team B. So what is the probability that team A will win the series in 6 games, all right? And what is the probability that team A will win the series? So let's do part A first. So part A is a simple, either you substitute into the expressions here, all right, with the relevant this. But I think it's better to do it on first principle. So again, if this is the A's win, so you put the A at the 6th game, and then there are 3 A's that you need to put in 1 to 5, right? Because A would win 3 games out of the 5 previous games. And then there are 2 empty slots, and that you have to fill it in for B. So basically, you do it this way. So, so now 5, 2, 3 is to place where the 3 wins A is. And then, so this would be 0.55 to the power 3 for the 3 wins. But the final game is also a win. So this is raised to the power 4. And the other 2 slots out of these 5 slots is where team A lose. So I will have 1 minus 0.55, and then I have to square it, and so it works out this way. So the required probability is x equal to 4. This is the best scenario. I mean, it's just 4 straight wins for team A. or 5 win, 6 win, and 7 win. And so I will have this, all right? Now you might want to, of course, you don't want to do it by hand, but now team A is a stronger team. Suppose it is not 4 wins out of 7, but suppose it is 3 wins out of 5. You will see the probability of A winning the championship. You might want to calculate this. Okay, and then calculate the other one. Suppose now, but this is just hypothetical, they are going to play 101 games, and then the team that wins 51 games will be declared as the winner. And then you still want to calculate the probability that team A will win. And you compare your answers for different scenarios. Okay, now the point I want to make is, if the team A is a stronger team here, the more games it will play in whatever convention it is, it will favor the stronger team, because the stronger team will eventually show its color that it is a stronger team if we play more games. All right. So you might want to do the calculations for 3 games out of 5. And then now you have 4 out of 7, and to calculate a ridiculous situation is 51 games out of 100, and you will see the pattern popping up. All right. Okay. Sharon and Anne play a series of backgammon games until one of them wins 5 games. And so suppose the games are independent, and the probability that Sharon wins a game is 0.5. Okay, so they are not fixing how many games, but they have to play 5 to get 5. So this is the same as playing at most 9 games, because by the 9 games, the winner would have been declared. All right, the worst situations. And the best situation is, of course, after 5 games, the winner is decided. Okay, and so we can calculate this. All right, so I would just, all right, so there is a little twist here. The twist is not asking whether Sharon will win, like Team A as before, but actually the game will end. When the game will end, it means that end at 7, so it means that either Sharon wins the best 5, the 5 games, or Anne will win the 5 games. So that is why they have to calculate 2 pieces. This piece is for Sharon to be the ultimate winner, and this is when Anne is the ultimate winner. All right? Okay, so so you have this. And that, okay, we are interested in this. Let A be the event. If the series ends in 7 games, meaning that Sharon or Anne will accumulate 5 wins at the end of the 7th game, then what is the probability that Sharon actually wins? So this is actually phrased in this conditional probability. So A is, I think if I were to do the problem, I would use S here and then A for N, all right? And so basically this is, or B is the, a winner is decided at the 7th game. So here so this is the usual trick to unconditionalize it, all right? So recalling the definition, that would be the probability of A intersect B over the probability of B. The probability of B has been calculated in part A before, and actually the numerator is referring to that Sharon is wins, and we actually have the number too. earlier, all right? And this is this number, all right? And so as a result, everything is actually there. And so this is 0.71. Okay. So that basically ends the Bernoulli family. So we have the Bernoulli trial. Just do it once. And the trial only has a binary outcome in which you either think of it as success or failure, which is easier to think. But we also label it as 0 or 1 because later on we want to add them. The binomial is a general situations of the Bernoulli. We have a specified number of trials, and each trial is a Bernoulli trials. And I assume independence of each trials, and that the probability of success is not changing. So the usual jargon later on in our subsequent module, subsequent part of the lecture in this module would be independent and identically distributed, all right? So basically, each trial is independent of the outcomes of the other trials, so the independence. And then identical here means the probability of success is always the same. Now, of course, this is can be challenged because, I mean, let's say back to the NBA basketball team. I mean, they would learn a lesson from the previous game, and so it is not quite independent, and also the probability of winning might also change because some of the players might be injured, and so or some of the players that were injured in previous game, but now they are fit enough to play. So there are quite a bit of assumptions hidden under our calculations earlier. So this is something new, which is called a Poisson random variables. In a way, it is it's still very closely related with the binomial. We will see why in the limit. All right. So experiments using numerical values of a random number variable x, the number of successes occurring during a given time interval or a specified region are called Poisson experiments. Okay, if you don't like this, it's okay. I mean, in my career, this is my first time to hear Poisson experiments, all right? So basically, we are not, in a lot of Poisson applications, we are interested in something what we call a rare event, like accidents, all right, at a road junction. Now, you don't hear it, you don't have accidents a lot. So now, what do we mean by rare? Rare is relative to the time. Suppose within 1 minute, the situation of having an accident is small, all right? Of course, if you look at it for 1 hour, it might not be small anymore. So basically, the time frame would be shrinking, all right? So we will think of 1 hour, 5 minutes, 1 minute, or 1 second, and so on. So when your time interval is very small, within that small time interval, there are only two possible situations. Either you have no accident or you have one accident. Now, we count accidents as it's not the number of people injured. That might be more than one. But if you just count how many collisions, that would be only one such count, or there is no such count in this particular thing. And we are interested in accumulating it over a longer period of time, say an hour. But each individual split second, you have either one accident or no accident, all right? Now this, the Poisson experiment was first applied, but I believe it is more like a mathematical statement from Poisson, who is an eminent mathematician and probabilist. But the first people who apply it is in telecommunications when phone lines are actually arriving at the call center. Now, if you divide the time very, very small, for a very small time period, there is either no phone call calling in, or there is at most one call, all right? So that is the situations here. Okay, for a given time interval t, which may be of any length, such as a minute, a day, a week, or a month, or even a year, a Poisson experiment might generate observations of the random variable x representing the number of telephone calls in an hour received by an office or a call center nowadays, because you don't want to put the guy on hold too long. Even though you keep having the recording, your call is important to us. I mean, and then you kept being on hold for 30 minutes. Then you hang up. Just before you hang up, your call is important to us. You really get annoyed, right? So, so they wanted to analyze this. Now, in a way, this is also a queuing theory, something related to some other things. So we have a service, but now it's in the call center, and how many calls are coming in. So you have to design how many people are at the call center to answering the phone call. All right. The specified, now this is just a time length, but I can think of it as a region, as like for example in a plane or in a field. I wanted to find out how many, I mean in a very, very large place like Sumatra, how many hotspots are there? I mean fires that are burning. So this kind of modeling is also very similar to the Poisson case, but we are not looking at a line, but we are looking at a region. Now this region can be in dimension 2 or can be in any other dimension, I mean dimension 10. So it really depends on the modeling part. Now one of the things is the number of typing errors in a page. We basically, these are what I was relating, a rare event. We don't make typing error a whole lot, but there are situations that we do, and so for this kind of situations, we are modeling this by a Poisson random variable. So properties of Poisson experiment, the number of successes, I think it's better to think of it as accidents occurring or typos, all right, occurring in one time interval or specified region. So it's not just even one-dimensional, all right, but it can be any dimension, okay, in a region, independent of those occurring in any other disjoint time interval. So as long as your interval here and this interval here are disjoint, then the number of accidents within this time interval and this time interval are independent, all right? Or, I mean, this region and then this other region do not overlap, and the number of accidents in region A and then in region B are independent. So this is the situations here, all right? The probability of a single success occurring during a very short time interval or in a very small region, okay, is proportional to the length of the time interval or the size of the region. Size here is very small, okay, and the time interval is also very small, and does not depend on the number of accidents or typos occurring outside this time interval or this small region. Now, the probability of more than one success occurring in such a short time interval or falling in such a small region is negligible. So basically, it precludes multiple occurrences in a very small thing. For example, the example that I was referring to is the number of accidents at a road junction during a very short time period, or the number of typos within a very small region in on the page that you are typing. All right. Okay. So this is the form here. All right. The number of the number here. Okay. Of successes. Okay. I would change it to success now, but the successes usually in the Poisson case are sad things, all right? Accidents, death, that kind of thing. Or sometimes you can think of it as birth too, so that is a happy thing. Anyway, so success here is really in quotation mark. So we have these expressions, okay? Lambda is a constant that is fixed, and the x is changing here, the small x, all right? And the small x ranges from 0, 1, 2, and so on. It is a non-negative integer random variable, all right? So you don't have fractional part, all right, because it's counting how many situations. Here we probably won't bother you, but the expectation is lambda, and then the variance is lambda. Now, a rule of thumb later on, you will have two choices to approximate a binomial. One is we are going to use Poisson. Another is we are going to use normal approximations. Students usually ask, when should I use Poisson approximation, and when should I use a normal? When a gauge is Poisson, is that when the mean and the variance are the same. So when you are the things that you are trying to approximate, the binomial, if the mean of the binomial and the variance of the binomial are about the same, then it is legitimate to use Poisson approximations. But if the mean of the binomial and the variance of the binomial differ a whole lot, okay, then it's not justifiable to use Poisson to approximate this, and you should use normal approximations, all right? So we will come to this, I think, sooner or later, and then it will be revisited when we talk about the next chapter under the central limit theorem. Okay, so I think you are not keen about this, right? Okay, then why should I, right? Basically, they are using the Taylor expansion of the exponential function. So that is it. All right. So if you don't quite remember what the expansion, you just Google Taylor or Taylor-Maclaurin's series expansion of exponential functions. Then you will find out the series. All right. Now, but this is the calculation has a trick. The trick is instead of calculating expectation of x squared, we calculate expectation of x times x minus 1. This is because the denominator is factorial. So I want to do some cancellations. So that is where the trick is. If you use x squared, you will have x times x here, and you can only cancel one of the x with the factorial here. So this is a modification of the change. And so we have this. So I think let me emphasize this one more time. The Poisson random variable has this peculiar behavior that the mean and the variance are equal. All right? But it doesn't mean a random variable with the mean and the variance are equal. It has to be Poisson. So this converse is not correct. All right? But if we know it is Poisson, then the mean and the variance is agree. Okay, so you can read about Poisson. Okay, so these are some examples. Number of spelling mistakes one makes while typing a single page. Number of times a web server is accessed per minute. Again, the per minute is actually accumulation of very, very short time interval. I mean, maybe per, second or per fraction of a second. So per fraction of this, when the time is okay. so it would be reasonable. I mean, if you think of this, you go back to this situations. Basically, it is like this. Okay, part 3. All right, the probability of more than one success is negligible. So multiple occurrence of certain things within a very short time interval or a very small region is negligible. Okay, so the number of animals killed found per unit length of road is, again, if you make it really, really short length, it is either 1 kill or no kill. All right, so the number of mutations in a given stretch of DNA after a certain amount of radiation of exposure. So again, you look at it for a very short stretch, so each one is small. The number of unstable atomic nuclei that decay within a given period of time in a piece of radioactive substance. The distribution of visual receptor cells in the retina of a human eye, light bulbs that burn out in a certain amount of time. Okay. The number of robberies in a day is 4 in a certain big city. What is the probability of 6 robberies occurring in 2 days? So now in this case, the first step is to use the modeling here. So we will model the number of robberies in a day in this given city to be a Poisson random variable. And since it is given that the average number is 4, and the mean of a Poisson is lambda, and so now it just gives you the mean of the random variable is 4, so lambda is equal to 4 here. So this is it. All right, the rest will be just doing the calculations. The question, there's a twist here. In 2 days rather than 1 day. So because of independence, this day on the average is 4. This day is also average of 4. So the sum of the robberies in 2 days would be the expectation of this plus the expectation of this, so which is 8 here. So we wanted to look at only 6 robberies, so below the average, and so I will have this kind of probability here. Now this is in a lot of situations. Sometimes, for example, in 2018, we know how many, accidents, car accidents, and then compare against 2017, the number of accidents. So one way is suppose you want to see based on 2017 as a reference point, whether 2018 has exceedingly more accidents, all right? So one way to do the calculation is I use the 2017 as my baseline, a Poisson, and then calculate the probability of having at least this number of accidents in 2018 and see whether the probability is very small. So if that is the case, then one is tempted to, draw the conclusion that there is a surge in car accidents in 2018 as compared to 2017. So this is one way to apply the situations. This kind of calculations is important to the policy makers because it might be people have forgotten about road safety, and so the government might need to, embark on some kind of a road safety campaign. So here now using I have uploaded some files, right? If you remember. Luminous, okay. 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 Okay, so there's a PDF file that is actually prepared by Dr. David Chu. He is my neighbor now in office. He had prepared sort of like short documents on using R. All right. In order to illustrate how the R is being used, he actually calculate the probability or some other calculations in the lecture notes. All right. But the number of slides might have changed, so the internal link here may not work very well. It might be somewhere plus or minus some slides. All right. Another one that is prepared by Professor Chan, the other lecture group. He uses Excel, so this is another way to compute the Excel command. So these are just some sample, but nowadays I think you guys learned by watching YouTube, right? So or some other stuff. So anyway, I mentioned a number of times I don't know a lot of this because I have an army of students doing it for me. All right. So there is another online facilities. Years ago, David Lane provided very good, online calculators. So you just find your own favorite, all right? So this is a binomial. So the binomial, you have to enter the n, and then he called it pi. So this is a I don't exactly know the notation. Probably it's the mean of the random variable. And then you can either choose the above. So this is what we call the upper tail. The red part is the upper tail. And then if you want to calculate the other side, is the lower tail, which is the blue. Or you wanted to calculate something between. So let's say 6. So you calculate this, and they calculate this here. So this is so let's suppose this is 6. All right. So now this is a binomial, and if you look at now, I wanted to illustrate the central limit theorem. So this is 30, and then this is 15. Of course, I might have to change it later. It doesn't work. I don't know. But anyway, well, it's a surprise. Okay. So now the R command is there is a stamp in the R command. POIS is for Poisson. And then X is the number that you are calculating. D stands for density, all right? And P is the left tail probability, cumulative distribution function. And you have the lambda. Now, if you just key in, say, 6 and 8 in this order, then the R reads it as your X is 6, and then 8 will be your mean, or the lambda. But sometimes you might want to, but if you want to write down 8 here and 6 here, R will get confused. But if you type in lambda equal to 8, then it doesn't really matter where you put it in, because R will be smart enough to know that the 8 here, if you type it in this order, 8, 6, then they read it as the mean is 8. Okay, so I think we just keep on hashing this, all right? So I guess we can skip this. And also just this. the important thing is not in the solution because it's getting very repetitive. What is really more interesting is the story here. Okay, it's not because it is interesting story. It is a way of modeling. I mean, if you have seen how different scenarios are being modeled, then you will get to understand the situations better. All right, so I think this is it. And so these are the command. All right. Okay, so I will skip this. All right, maybe I'll stop here for a while and talk about the Poisson approximations to the binomial. And I think after this, we will be able to round up our discrete random variables, and we'll start on the continuous random variable. All right? So do come back at 11. Okay. Let's see. Okay. Let's start. We wanted to introduce a concept of Poisson approximations. Now, of course, I would argue that it's actually getting out of date in some way in the exact calculation of the binomial. But let me explain why this is out of date. It's already happened, I think maybe 10 or 20 years ago. The NUS library, if you Google it, if you search it, the library used to keep a binomial table. Now they put it in the, well, many years ago you put it in the closed stack. I think maybe now it's maybe go to the museum. All right. Because the table is pretty big. I mean, the book is actually a book. And then they give you all different n, and then different p, and then columns, all right? So the columns are for the particular k, and then give you the probability. Okay, and you also have to learn some tricks because if the p is not quite in the range, so you have to do some approximations here and there. But nowadays, I mean, you can use a graphic calculator as well as use online calculations. And if you have installed your R in, you can do the calculations without any problem. So these examples here, a little bit, maybe you think that this is a bit out of touch. But these are a good example in the sense that it illustrates the thinking process that why it is good to assume Poisson modeling. Another thing is, as I have mentioned in passing, that sometimes it is unrealistic to assume there are two assumptions in the binomial. One is independent. So each trial, the outcome of the binomial, the outcome of the 0 or 1 is independent of the other outcomes in the other trials. So we do have independence. And then the probability does not change from trials to trial. Now this part may be a little bit, can be relaxed. And that part is what we call now, if you Google it, it's called Poisson binomial. The individual p might change. And we actually now have results saying that even the trials are slightly dependent. We have some way to quantify it. It is still, Poisson still work, or the binomial still work in some way. So that is where it is interesting, because it actually relaxes the assumptions pretty much. Now, you might think that this is rather ancient, because Poisson thing and the binomial thing has been around for a long, long time. Poisson, I think probably we are talking about 100 years ago. And binomial would be further back. The Poisson approximations of this kind of Poisson binomial is turned out to be quite recent. It's around 1970s, all right? And it has a special meaning to NUS because the method is actually called Chan-Stein method. The Chan is one of our senior faculty member, Louis Chan. Now he has retired. So he make it, put Singapore on the map in this respect, the Chan-Stein method for Poisson approximations. So, of course, now we limit ourselves to the binomial case, which I think you think that it is rather redundant, all right? So in some way it is. But one of the, for Poisson approximations is this. Now, if P is close, okay, so okay. Poisson approximations to the binomial. Okay, I will spell out this in a real setting, why this is the case. Because when I first learned it, I just don't get it. But at that time,
I mean, in a British university, you don't ask your lecturer a whole lot. I mean, and very often we don't attend classes, all right? And then there's no web class. And one of the exam, usually we only have 3 people in the class. And then the exam come, we quickly count how many students actually enroll. I mean, then we only at that point of time, we know how many of us are taking the modules. All right, so now I will explain to you why this is the setting. But the theorem is saying that this is converging to something like this. Now, I think there is a typo here. It should be lambda. All right, change it to lambda because your n has already gone to infinity. And p is also changing with n, so you should replace it with lambda. E to the power minus lambda, and then lambda to the power x. Now the thinking behind is very similar to this. And so the thinking is you have a fixed time interval, okay? So say 0 to t. And now first you break it into even number of intervals. So this is the first interval, and then this is the nth interval. And if the interval is very small, the focus is, so it's only focusing on a small region, all right? So that's why you didn't see it. Now, so we have this. So you think of phone call. How many phone calls are coming in the time interval 0 to t? And if you divide it very, very finely, the length is n, t over n, then you basically either 0 or 1, a Bernoulli situation. Because the assumption is you basically have no batch mode coming in. I mean, the phone calls are, this is realistic in telecommunication, but I mean, if you are thinking of a server, I mean, you might have a batch mode of files coming in. So anyway, this is not my expertise. So anyway, so we have this, and that is why the probability of with it happening would be something like proportional to 1 over n, all right? Something like this. And so that is why p is somewhat like lambda over n when you divide your interval finer and finer. So that is why the Poisson approximation insists this, all right? In fact, we can change it to np converges to lambda. It doesn't really matter whether you really have to be equal or equal to lambda. So that is the background behind. Okay. So, but this typo you really need to change because it doesn't make sense. So the defective items. Suppose that the probability that an item produced by a certain machine will be defective with 5%, and find the probability that a sample of 20 items will contain at most 1 defective items. Now this is actually a binomial, so we can calculate the binomial. But I think what this slide or this example is trying to illustrate is how good the approximation is. So the probability of x less than or equal to 1, this is the exact probability, all right? But if we are calculating this with a Poisson here, now the Poisson, the choice of the lambda has to match the mean of the binomial, all right? The mean of the binomial is n times p, which is 1. So you have this. So you will see this is the approximate value, and this is this. So I think it matches up to the 4 decimal places. So so here n is not very big. Okay, and yeah. Now, one of the rule of thumb is this. It's more than a rule of thumb, but this is a known mathematical fact. For a binomial, the mean is expectation of x is np, and the variance of x is np1 minus p. So if p is small, the variance is equal to this. So in other words, the mean and the variance are almost the same. And this is where the setting for the Poisson, because Poisson has the same mean and the same variance. So that is exactly the situations here. Okay, so but of course, the fact that it is so accurate up to the 4 decimal places, I mean, if I haven't done the calculations, it surprises me quite a bit. All right. Okay. So here you have the actual calculations. It is actually not accurate up to the 4th decimal places, but because of the round off here, so they agree up to the 4th decimal places. In fact, they only agree up to the 3rd decimal places. All right. Okay, the probability P of an individual car having an accident at a junction is this. Now, this P is really small, and it should ring a bell that the Poisson would be a good approximation. If there are 1,000 cars passing through the junction during a certain period of a day, what is the probability of 2 or more accidents occurring during that period? Now, so the actual modeling would be a binomial. Of course, we assume that whether a car has an accident has no effect on the other car. All right, this can be challenged. All right. Okay, so you can do the calculations according to the slide. This is difficult to use for hand calculator. All right. Now, one of the other things that your hand calculator can be difficult is when your n choose r, when n and r are quite big, and your calculator has certain limit on the factorial. All right, but I think this is now not a big problem nowadays, and so but the actual probability that we can calculate is this is 0.5%. All right, okay. And so we have this. And now the first thing is to pick a Poisson approximations. The Poisson is only need one parameter to fix it. So, and that would be the lambda. And the lambda is the mean of the Poisson. So the mean of the Poisson, in order for you to have a good approximations, you want to match the mean of the binomial. And so and this works out to be 0.1, and so you have this, all right? And you can easily do this with your handheld calculator, all right? And we can compare it. The accuracy is up to the 5th decimal places. In fact, this is a mathematical fact which you probably don't know now. The smaller the p is in the binomial, the better is the approximations. And it has nothing to do, in some way, with the n. All right. So even when your n is small, as long as your p is very small, the approximation is pretty decent. All right. But of course, when your n is small, you do it by hand. All right. Okay. So in a manufacturing process in which glass items are being produced, defects or bubbles occur, occasionally rendering the piece undesirable for marketing. It is known that on the average 1 out of 1,000 of these items. So again, the probability of success is really small. So we are in the good setting for Poisson approximation. What is the probability that a random sample of 8,000 will yield fewer than 7 items possessing bubbles? All right. So here, even with your calculator, handheld calculator, it takes a while to do the calculations here. Of course, if you have a graphic calculator, this is easy. All right. Here he is using Poisson. All right. Let's calculate the binomial and see how accurate it is. It's annoying because I can't set it. So you want a binomial, right? So the stem is binom. And you want it to be 6. And then, and your n is it 8,000 and 0.001, 1 in 1,000. Okay, so this is the answer, 3132521. It's a nice number. Okay, 3132. So it is accurate up to the the third decimal places. So this is a fairly reasonable calculations. All right. Now here I've been keep emphasizing the p is small. Okay. There is another part of the story when p is very big, meaning that very close to 1. Now here the trick we use is we are talking about the probability of success is small in the previous slides, but by a change of labeling, I think of success as failure, failure as success, then I can handle p is very close to 1. Because when p is very close to 1, the probability of failure, which we now deem it as success, will be 1 minus p, which will be very small, right? Because p is close to 1. Okay, so the trick would be doing this way. So if x is binomial np, and p is very close to 1, then n minus x is to count how many failures. So this will be your new y, and this would be still binomial. But now the probability is 1 minus p. And this is now, you approximate this. So for example, you wanted to approximate this. Okay. For example, you wanted to approximate x less than or equal to m. And under these situations, p is close to 1. You can't use Poisson approximations. But you can think of it this way. All right, so the number of successes is no more than m. So in other words, the number of failures should not be less than n minus m. And now I call failures as success. So this would be approximately equal to the Poisson, bigger than n minus m. And then the lambda here that I want to match would be n times 1 minus p. All right, so that would be the trick. So basically, you reduce the problem to another binomial, but now you look at failures instead of the successes. All right. Okay, so the Poisson is actually applicable on both ends, either very close to 0 or very close to 1. When p is somewhere in between, in the middle, nothing you can do, and that would be the normal approximations. Okay, so when p is moderate, not very small, not very close to 1, normal approximations will be the choice. Okay, now I think we have gone over all the discrete random variable, and we wanted to talk about continuous random variables. I think we will talk about uniform, similar to your discrete case, and then we'll talk about exponential. Then we will talk about normal distributions. There are many other distributions. The chi-square that will be coming up in the next chapter, and then the t distribution and the f distributions will be mentioned in subsequent chapter. Okay, so uniform distributions is given by this. Graphically, okay, maybe I'll explain the graph first of the density function. So the density function is actually this. It is uniform because over the interval AB. So when you say something is a uniform distribution, you have to provide the two endpoints where it starts and where it ends. So it's starting at A, ending at B. And when it is uniform, it means that the density function is constant, all right? Okay. And so this is this. And now, if you remember the expectation is just looking for the center of gravity. The center of gravity will be right in the middle, all right? So that is why is the expectation is the center, okay? Okay, because it is you are thinking of a rod that is of uniform density onto the endpoint, so the center of gravity has to be at the middle point. Okay, and the variance is something proportional to the, maybe I should say the standard deviation. The standard deviation is taking the square root of this, so it would be proportional to the length of where the uniform distribution is. So it would be proportional to B minus A, all right? And the variance is a square. So the factor 12 is kind of characteristic in the uniform distributions. The frequent one that you usually use is A is 0, and then B is equal to 1. That is our familiar uniform distributions, and so on. Okay, so I'll leave the calculations to you. This is how it is done, but another way to redo it is this way. Okay, so if X is uniform over AB, one way to think about it is if I move my origin, X minus A, so X minus A now will start at 0, and I scale it, B minus A, that would be uniform, 0, 1. So I think if you do it this way, by assuming A is equal to 0, B equal to 1 in the slides, your calculation is easier. All right? Now once you have your, okay, so this is Y. So for this particular case, the expectation of Y is half, and that the variance of Y is equal to 1 over 2, 1 over 12. And so now you can translate back your here expectation of X by doing the algebraic calculations here. This will be the same as A plus B minus AY. And so this would be A plus B minus A expectation of Y. And so this would be A plus B minus A over 2. And so this would be A plus B over 2. And then the variance of X would be the variance of A plus B minus AY. And remember that when we have a translation, the variance will disappear. All right? And so we have B minus A square, variance of Y. And so that is where the 112 comes about in your slide there. All right, so so these are some little tricks here and there to reduce your calculations. But this is actually how you would do it. Suppose you have some way to, you guys are from computer science. One of the things is to generate a random number. All right, a random number generator. If you are able to generate a random number between 0 and 1, you would be able to generate any random numbers in this interval. The way to go about is if your Y is something between 0 and 1, then you have A plus B minus A times your Y. And that would be the one that you generate this. So this is actually how you would do that. So if you are able to generate something like here, then to generate something, it would be A plus B minus A times Y. So you will be able to translate it, all right? Now, in fact, this is all you need. Later on, we know that if we are able to generate a random number between 0 and 1, we'll be able to generate all other distributions. So I think the real difficulty nowadays is how to generate a really true random number generator. All right. So once you can get over generating something between 0 and 1, you will be able to do it for all the others random variables. So there are tons of tricks, but so what hinges on is whether we are able to generate something really random between 0 and 1. All right, so we skip this. So the idea is every interval is equally likely. So this is justified in this way. Okay, so this is after integration. So when a is 0, b is equal to 1, it would be equal to x, all right? So, so it is just this. All right, so we see this, and we have this. So a point is chosen at random on the line. At random here, I mentioned it. It is our jargon saying that it is uniform, all right? So what is the probability that the chosen point lies between 1 and 3 halves? So we have this, all right? And so we use this. Of course, now it depends on which one you use. Either you use this to start your starting point, or you can actually use this as your starting point too. Okay? So a is 0, b is equal to 2, and then x is equal to whatever you want. So it would be f, the big F, at 3 halves minus the big F at 1. So you can just use this, then you don't need to do the integration. So it is really up to you because it has been done earlier. Okay. Buses arrive at a specified stop at 15 minutes interval, starting at 7 a.m. So these are the time. If a passenger arrives at the stop at a time that is uniformly distributed between 7 and 7:30, find the probability that he waits less than 5 minutes for a bus. All right? Okay. So X is the arrival time of the passengers after 7 a.m., and everything is measured in minutes. So, and his arrival is somewhere in between 0 and 30. So it is this. And so the passengers wait less than 5 minutes means that the bus that he can only take would be 7:15, right? Or the bus that he will take is 7:30. The bus at 7 o'clock, he will miss the bus at 7 o'clock. All right? And so this is the calculations here. All right? Okay, a point is chosen at random on the line segment L. Okay, interpret this statement and find the probability that the ratio of the shorter to the longer segment is less than quarter. Now, you see the subsequent slide. The calculation is a little bit difficult, not because of the problem. It's because there are different situations, because it is always the shorter one over the longer one. So it depends on where you, the break point of the line. If your break point of the line is on the left-hand side of the middle one, then the left-hand segment is the shorter one. So that would be the shorter one, the left one over the remaining one. All right? But if the break point is on the right-hand side of the middle point, then the shorter one is your right one, rather than the left one. And so you will be using the right one over the left one. All right, so this is the formulations. X is uniform here. So X over L minus X is the left side over the right side. But it may not be the shortest. There is another possibility is the shorter one is the right hand, which is L minus X, right? And over X. So this is it, all right? Now another trick, so these are basically some mathematical trick here. To calculate the minimum less than certain thing is very difficult because it might happen that this is less than here or this is less than here. But you might have some, okay, in this situation it doesn't happen very often. There might be some overlap between the situations, okay, the two events. So the usual trick is to look at the complement, all right, the opposite. Because if the minimum is, if you wanted to, you can change it to bigger than or equal to. You add the equal sign, but it's not going to affect the calculations. All right? So if the minimum is bigger than or equal to 1/4, then everyone else has to be bigger than or equal to 1/4. So this is the gist of it. All right? So once you have this, then you can solve this inequality. So the first one leads to x bigger than L over 5. And this is this, all right? Okay, so so after this, then now because of uniform, you don't need to do the calculations because it would be 4 L over 5 minus L over 5 divided by L, all right? So which would be 3/5 of L over L, and so you have 3/5. And so as a result, 1 minus 3/5 is 2/5. So this is just a twist of the problem, not just the uniform distribution, but it is actually things that are related to the uniform distributions. Exponential distribution. So I'll try to go over it and then, okay. And maybe I should stop here. Yeah, I will talk about exponential distribution on Friday, and also the normal distributions also on Friday. And I think that would probably wrap up all of this. Then hopefully we will start a new chapter next week. All right. So from next week onward, we are more interested in trying to know the populations. Knowing the populations is by sampling, and so we need to know a lot about how the sample behave if I have done it right. All right. So maybe we'll stop here.